again. This one is also a continuation of the first discussion. Now, if I then have some current I, which we now have as being measured in amps, that's equal to the motion of the charge over time. And I'm going to take this and look at this in a couple of different ways right here, since we have that opportunity. The current's kind of an absolute number. The size of the wire, hey, maybe a big wire, you would need, if there's more room for the electrons to move, so to speak, over a certain change in electric potential, the wider the wire, the more easily they will move. So I want to define this, I want to define a new term. The current density, J, and I'll write that in terms of the current over the cross-sectional area. Now, if I look at this, if I have some change in potential between two cases, the one I'm going to have is that is going to establish an electric field inside the wire. Yes, when we looked at conductors, if the charge is not moving, all the charge will end up on the outside of a conductor. If I have a change in potential, then I can have moving charge and therefore an electric field inside the conductor itself. Now, the stronger the electric field, the greater the force on an individual electron, and then therefore the greater the current. So, this current density is proportional to the electric field. Well, I'm going to define that current density as being equal to some quantity, sigma, times the electric field. As an aside, electric field is a vector, and properly speaking, the current density is a vector as well. For the examples that we're going to use, when we're looking just at, say, a wire, well, heck, in that case, we can treat it as a one-dimensional problem. That's one of the advantages of using a wire as a simplifier in this case. And so we will, much as it pains me to do this, just treat, 4, 1 dimension. Now this is the conductivity of the wire. So, that conductivity is defined as the current in the wire divided by the electric field in the wire, and also divided by the cross-sectional area, which let's see, will come down to, which I can also write with the material we had just set up, that I can write this as, okay, the current density, the current, I can write that as the charge on the electron, E, times the electron current, the density of free electrons, times E times tau, the mean time between collisions times the cross-sectional area, divided by the mass of the electron, times the electric field, divided by the electric field times the area. And I can get then what's useful here is I can get a conductivity that is material specific. The details of how, oh, okay, the electric field in the cross-sectional area cancels out, that's lovely. But why that's useful is it comes down to a material specific thing. And the reason why this is good is because then we have something we can then make a list of things in the class in the textbook that says, for iron, the conductivity is thing. For aluminum, the conductivity is number. And so on like that.